Okay, thank you for the introduction. My name is Simon Eberz, and I'm here to talk about our work on predicting biometric features across contexts. So this is joint work with Julie Lovisotto, Andrea Patana, and Marta Kwiatkowska and Eva Martinovic from the University of Oxford, and Vincent Mendes at Swiss. So first of all, let's hope this does something. It does not. Maybe this one does. It does. OK. So I'm sure we all know that any sufficiently popular system will also eventually be subject to various attacks. And the same is true for biometric recognition systems. This did not actually do. It does work on the screen here. It does not work on the screen there. They seem to be not synchronized between this screen and this screen. Ah, it does. OK, so let me show you a few attacks on biometric systems. So the first one we can see on the top left here is an attack on touch dynamics authentication. So the idea of touch dynamics is to harvest user behavior when they use a touchscreen-enabled device, such as a smartphone or tablet. And in this case, it's not actually a user carrying out these swipes, but a purpose-built Mindstorm robot that imitates the user. On the top right, we can see an attack on gait recognition. So gait is human walking style, which is normally measured through accelerometers. And in this case, the attacker is imitating a user using a treadmill, which allows to more easily control certain gait features, such as step width and foot angle. One approach, again, for authentication is keystroke dynamics. So humans generally exhibit somewhat distinctive typing patterns. And in this case, it's a paper at NDSS 2013 that allows the attacker to train themselves to more closely mimic the victim. So in this case, what we can see here is the system giving feedback to the attacker regarding how close they are to the victim. Lastly, and this is an attack I presented at NDSS last year, which is an attack on a NIMI band, which is an ECG-based authenticator. So ECG is human heartbeat patterns. And in this case, we injected a forged ECG signal into the NIMI band through a waveform generator. So all of these attacks are generally split into two phases. First of all, the attacker collects some of the victim's biometric data. And in the second stage, this biometric data is then injected into the actual sensor. So this attack can either be a mimicry attack or a presentation attack, depending on the kind of system we're trying to attack. So as you may have seen, all the work I talked about earlier, which obviously is only a snapshot of the entire body of work, the authors generally make the assumption that the attacker already knows the biometric information. So the focus of our work is actually to solve this first stage, to analyze where exactly an attacker might be able to get this biometric information in the first place, and how we can measure how useful data in the wild might be to an attacker. So to outline our threat model, so we talk about these cross-context attacks. The rationale behind all of this work is that a variety of commodity sensors actually leak biometric information constantly. So these four biometrics I talked about earlier can obviously be used for authentication, but the same behavior also occurs on a daily basis when users interact with devices. And this leads us to the threat model we assume. So we have an adversary in the middle, and we have our victim on the left. So the victim has a smartphone, which, just as a running example I will use throughout the presentation, does gait recognition. So the smartphone has an accelerometer, which constantly measures this data. And based on this accelerometer data, it tries to recognize its owner's walking style. And if we have a mismatch, then the smartphone will be locked. So naturally, the adversary wants to attack this gait-based authentication. And the problem is that he then needs to learn the victim's biometric information so that he can carry out an attack like the one I showed earlier. However, we assume that the smartphone, with its purpose-built gate-based authentication, is actually secured. So we can't simply steal the data on the device and use it to carry out our attack. However, the victim also conveniently uses a smartwatch. So the smartwatch also has an accelerometer, for instance, for fitness tracking. And this might be less secure, mainly because it does not actually do authentication itself. So maybe the developers did not think to secure it adequately. For instance, the victim might also share sort of fitness information on social media platforms, or maybe there's an unsecured wireless link available to the attacker. So now we might say, well, the paper is over because the attacker simply takes the data from the smartwatch, uses this treadmill attack to attack the user's phone, and the user has lost, and there's nothing we can do about this. Actually, no. So let's again consider our victim over here. The victim is carrying a smartphone. In this case, maybe our victim is going for a run and has a smartphone on this arm strap. So the smartphone constantly records its accelerometer data, which might, for instance, look like this. So here we can see real data collected over a number of gait cycles. And we can see that there's a certain pattern which makes up the biometric features. Now the attacker wants to have this data, but he can't get this data because it is actually secured in the device template storage. However, our victim also has a watch, which does have data the attacker can get to, but suddenly this data looks very different, and that is because the position and type of the sensor actually affects the signal and the resulting biometric features. The same might be true if we have another fitness tracker that is worn as a chest strap, which can also record accelerometer data, which gives us yet another signal. So in this case, sensor type and location define a context. So a context might be something like a smartwatch being carried by a person while that person is walking. And we have feature distributions that very strongly depend on the measurement context, as we can see on this plot here. So each device generates a pretty unique trace of accelerometer data. And what we want to figure out in our paper is whether these cross-context changes are systematic across users. So if we can use one context to predict another, which then in the end would allow the attacker to actually use the smartwatch data. So our goal is to calculate the predictability of features across contexts. And we do so by learning these cross-context changes, so the difference, for instance, between the smartwatch and smartphone data based on population statistics. So if we reconsider our initial threat model, which has the attacker obtaining data on the smartwatch and wanting to impersonate the user on the smartphone. We extend this threat model as follows. So instead of simply getting the smartwatch data from the victim, we also consider population data, which is what you can see on the right. And the most important thing to note is that the victim is not actually part of the population. So in that sense, it does not make the attacker stronger in what he knows about the victim. And in this population, we consider pairs of information between the source and the target device. And as you notice, this security measure lock is missing on the right-hand side on the phone. That is because this population can be the attacker's friends or relatives and so on, so that they give the data willingly to the attacker. And based on these pairs of information, we generate what's called a transfer function. So this is a function that takes one distribution of features and transforms it to another. In this case, we transform source data to more closely look like target data. So this is something we learn based on population data, and this is something we do once. And this is a universal function that is not specific to the victim at hand. Once we've done this, we can use this function and apply it to the source data that we've collected for our victim. And this allows us to calculate what is a good approximation of what the data will look like in the target context, which then would allow us to attack the phone. So let me show you how this actually works. So the goal of this transfer function is to minimize the distance between the source and target features, or more specifically, their distributions. So this is what we do, formula. First of all, we consider a space of possible transfer functions. So each of these functions transforms one distribution of biometric features onto another. And in our work, we consider linear functions, but ultimately our work found that it doesn't make a great difference which type of function we use. So this is an optimization problem, and our optimization objective is to minimize the distance between this. So we apply this candidate transfer function to a set of source features, and we compare this to the distribution of target features. So all of this is done based on the population data. So in that case, we do actually have this data pair. So we have the source and the target features. And we compare these two simply based on L2 distance. So we want to find a transfer function that minimizes this error. And this is something we then average over the entire size of the population. So we want to find a single function that works for all users in our population. So based on this transfer function, we calculate something we call an Unpredictability Score, which is our newly introduced security metric. So we have the score on the left here. This score is specific for an individual biometric feature. So we compute one score for each feature that is used by a certain biometric recognition system. And this is based on the error of this transformation function. So on the previous slide, I showed you this distance measure between our predicted and actual feature distributions, and that is the error we are talking about on this slide here. This is calculated then for each feature and for each user, but obviously this is going to be a quite high number of scores we get, and then to have the thing a bit more manageable, we compute what we call a feature score, which is simply these unpredictability scores averaged over all users in our data set. So that tells us exactly how predictable an individual feature is, but we also want to learn how this relates to a biometric level. So that allows us to compute something called a source target score, which is simply the feature score averaged over all features. And because some features are more important than others, we weigh this based on relative mutual information, simply to show that more distinctive features are being given a higher weight. So overall, a lower score means that our transfer function gave us a closer approximation of the target context, which means the features are more predictable and the system overall offers lower security. So you can think of the unpredictability score as a security score of our biometric. So we wanted to validate this framework with a bit of real-world data, and the first thing we found was that there's no available data sets that actually consider several measurement contexts. So while there is biometric data sets out there, they're always measured on the same device, in the same environment, and so on. So we fixed this by collecting data for 5 biometrics: eye movements, mouse movements, touchscreen inputs, gait, and ECG. And for each of these, we considered a variety of contexts, such as different devices, sensor positions, and so on. So we collected this on 30 members of the general public. To account for time stability of features, we measured this in 2 sessions, which were a couple of days apart. We also share this data set online, so if you do work in this area, please do have a look. It is free for any use in research. Okay, naturally, we have a lot of results. This is a small snapshot of our results, so we'll only give you the most interesting sound bites. First of all, simply to zoom into the biometric level results, we can see that for some biometrics, things are easier to predict. So in particular, you can see these overall scores on the left, which are lower for eye movements and touch dynamics and higher for gait. So that tells us that gait is actually a biometric that's very difficult to predict because the changes in features are very unpredictable between different contexts. So it's actually not that easy to take the smartwatch data and predict the data that will be measured by the phone. We can also see that when we use data that is not particularly recent, so gathered in a different session, the attack becomes harder as these unpredictability scores go up. So ideally, for an attacker, it would be better to gather this data close to when the user actually enrolled in a system. We can also see that to zoom into one biometric, which in this case is ECG, that some sources are giving us more meaningful data. So that is because they're actually conceptually fairly similar to the authentication context, which then makes this prediction a bit easier. So this is actually, again, confirming the results of our NDSS paper from last year, which showed that the success rate of attacks was higher for these particular sources of information. To give you a brief glimpse into biometric features as well, so this, in this case, is for touch dynamics, so for how users use the touchscreen on these devices. We can see that for some For some features, different sources are much more useful. So in this case, we consider what we call a low-end and a high-end phone as sources of information. And we can see that the high-end phone gives us lower unpredictability scores. So in this particular case, this is a result of differences in sensor quality, specifically with the resolution of the area sensor in the touchscreen. So that shows that integrating better quality sensor in these devices not just improves the normal error rates that our biometric would have in the first place, but also makes them much more resilient against this kind of attack. Just to wrap things up, so we proposed a framework to measure the cross-context predictability of biometric features, and this allows us to gain information both about individual features and complete biometrics. So the main uses we would like to see for this new security measure is first and foremost to compare biometric systems. So we can say that one system might be easier to attack than another using these cross-context attacks. Within a biometric, we can also identify particularly vulnerable target contexts. So this might mean something like this device should not be used for authentication because it is very easy to attack based on data collected in different contexts. We can also figure out which sources of information are particularly useful to an attacker. So these are sources that maybe we should guard more closely as to not compromise the security of our authentication system. We can also use this to identify particularly strong or weak features, which is useful when we actually want to build a more secure biometric. So we might be incentivized to use features that are less easily predicted across different contexts. So to remind you again, the dataset is available online. The link to the dataset you can find in a paper, which you are very much encouraged to read. For future work, we mainly want to look into how we can engineer stronger features. So is there something we can do either to the features or to the hardware of a collection system to make features as unpredictable as possible? And with this outlook, I would like to conclude my presentation. I'm looking forward to your questions. Thank you.
Vinny Monaco, Darwin Research Laboratory. Really nice work, and thanks for making the data set available. And can you comment a little more on what would make a context vulnerable or not, or resilient to this kind of attack? Perhaps it seems that there's this temporal dependence or a certain amount of perhaps entropy that comes with a user, or lack of entropy coming with a user resting, for example.
Yes, so it's two components basically. One is if the uniqueness within a certain context is already low, it makes it easier to predict. But on the other hand, it is also similarity to different contexts. So I think this is particularly visible for this ECG data I talked about. So the closer the authentication context is to the source context, the more likely you will be to get lower unpredictability scores. So on the first slide, I talked about this NIMI band, which is this wristband that does ECG-based authentication. And this was very easy to attack if you measured ECG again on a person's arm rather than somewhere else. So the takeaway of that could be, if you build an authentication system, make it as exotic as possible to make sure that all normal sources of biometric information are as far removed from this as possible.
Very interesting. Thank you.
Hillary Orman, Earth. All of these biometric things seem to me to be trying to take a pinhole view of very, very complex interconnected system, which we have great experience with and just don't understand, which is the human body. It seems to be a multidisciplinary problem to try to engineer security based on this complex system. Do you think that working with physiologists and medical community and things would be beneficial in exploring advanced ideas?
Yes, I agree. So specifically when it comes to biometric features, some of the things are simply built on insights we already have from, say, medical domain, neuroscience, and so on. So this allows us to build features that we would in advance expect to work. I think this is kind of going out of the window when we talk about deep learning, because suddenly we don't understand anymore what actually makes things distinctive. But I think doing both is probably the most beneficial approach. So using both machine learning and expert knowledge about the human body and the biology involved is probably most likely to succeed.
Thank you.
Hi, I'm Max from the University of Arizona, and I'm wondering if the IMU, the inertial measurement units on the devices you looked at, were good enough to start inducing, maybe with a Kalman filter, the actual three-dimensional position of the arm over time, or whatever body part.
Sorry, could you repeat the question, please?
Yeah, I'm sorry. I'm just wondering if the accelerometer data at this point in time is good enough that you get from these devices to perhaps use a Kalman filter and figure out the actual dead reckoning, the three-dimensional position relative over time.
Yes, so it really depends on the actual sensor. So especially for some of the smartphones, we had extremely low sampling rates and overall resolution. But I think depends on which device you're using. So I think when you have off-the-shelf sensors and smartphones and so on, it might not be good enough, especially because these devices are not exactly built with authentication in mind. But with improvements in hardware, yeah, I would say that's possible.
Thank you.
Peter Neumann again, very quick comment. This is nice as far as it goes. Hillary just said, gee, this is a multi-dimensional problem. You haven't considered things like the gummy bear attacks on fingerprints and the contact lens on eyeball recognition and things of that nature. Can you expand your work a little bit to look at it sort of holistically in the large?
Yes, so in this work, we obviously consider specifically these cross-context attacks, which assumes that you get data from other commodity sensors and use them as a basis for the attack. So it doesn't cover something like attacks on fingerprints, which are static features, which I would expect to have a lot less cross-context variation. So in this case, if you take a fingerprint of a mug and present it to a sensor, it would be a very different kind of attack. So our work then allows to only quantify how resilient we are against cross-context attacks depending on some kinds of measurement data we have. But for more static features, this is not the right approach.
Okay, let's give another bigger round of applause to all the speakers.